Alright, welcome back to our Big O series. I'm Max Smith, and in this episode we are diving into Quicksort, one of the fastest sorting algorithms. But with a twist, the pivot choice can make or break it. We will talk about pivots later in the lesson. So, Quicksort uses a divide and conquer strategy. It picks a number called a pivot, then rearranges the list so that numbers smaller than the pivot goes to the left and numbers larger goes to the right. So, for example, let's say we have 12, 4, 5, 20, and 7. Let's say we pick 12 as our pivot right here. 12 is our pivot now. So let's work at 12 our pivot, and then we place 7, 5, and 4 to the left, and 20 to the right. Boom, sorted. Let's say, these numbers are going to be random because there's more than one. So it could be 4, 5, 7, 7, 5, 4, any of that. If it was that, then we would have to re-sort it. We'd pick one of these as a pivot. Let's pick 4. Numbers bigger, 12 and 20. And numbers smaller. There's something smaller. Okay, crap, hold on. Numbers bigger, sorry. Alright, here we go. 5, 7, 12, and 20. And that sorted it. So it just kind of depends on the pivot choice you make. That's very crucial. A good pivot splits the array roughly in half every time, giving Quicksort its best case and its average case performance. O n log n. Boom. Alright. So, what do you guys think happens when we choose a bad pivot, at least performance-wise? Let's think here for a second. So, if we choose a bad pivot, like always picking the first nearly sorted list, or array, suddenly Quicksort behaves like a quadratic algorithm with order n squared. So, let's do that as a visual. So let's do the same as we did last time. Let's do 12. Wait, that wouldn't work actually. Let's do 7, 8, 9, 10, 12, 13. Let's make that less big actually. Let's do 5. Alright, that's like very, very nearly sorted. Alright, so our pivot, we're going to pick 7. Alright, 7, 8, 9, 10, 12, 5. It's still unsorted, the same thing as last time. Alright, so let's pick new pivot, 8. 7, 8, 9, oh wait, yeah. Alright, 10, 12, and 5. But the 5 can also go. Let's do 5 here. Alright, next pivot, we can pick 9. 7, 5, 8, 9, 10, 12. And you just keep going on like that until eventually we pick 5 as a pivot, and that would turn to 5, 7, 8, 9, 10, and 12. Alright. So, to fix this, programmers use smart pivot strategies. One of them, random pivot, where we pick a random element instead of going in like this line kind of type thing. So, let's pick random out of this, pick 5, 10, 12, any of that, and that'd probably help faster. Next one is median of the 3, where we pick the median of the first, middle, and last elements. So, our last element 7, or I guess it'd be 12. Our first element's 7, last element's 12, and medium is 9. Alright, so we'd pick 9 as the pivot, and then keep doing that. Next, we do hybrid approaches. So we switch to insertion sort for tiny subarrays, which is faster for small sizes. So yeah. So Quicksort is still very fast in practice in most programming libraries like C#'s array sort. I'll draw that out for you. Array dot sort. Yeah, things like array.sort use clever hybrid strategies to avoid worst case performances, such as what we just did up there. So, how do you think these hybrid strategies work? I'll write it down somewhere. We'll cover it later in the lesson a bit. Alright, so after that, now we're going to talk about Quicksort in C#. I'm going to explain the code and we can run it. So, this right here is, begin with an unsorted array of numbers, 12, 4, 5, 27, 15, 3. As you can see, that's way out of order. So the goal is to sort this array in ascending order using Quicksort. This line right here prints the array before sorting so we can see what it was before we sorted it up. Next, this calls the sorting function and telling it to sort the array from the first index, which is 0, to the last index. Alright, right here, all this right here. This is a recursive algorithm, meaning it keeps calling itself to handle smaller and smaller pieces of the array. First, it checks that there's more than one element to sort. Then it calls partition to divide the array around a special number called the pivot, which we talked about. Everything smaller than the pivot goes to the left, and everything larger goes to the right, as we said. Finally, it recursively sorts the left and right sides. So, it's right here. Oops. Alright. So, this is where everything kind of begins. The array is arranged around the pivot, right here. And here we use the medium of 3 strategy to pick the pivot. So, talked about that already. Here. So, we temporarily move the pivot value to the end of the current range to make the next steps easier, right here. And then here we go. This part. Now we loop the elements. Each time we find a number smaller than the pivot, we move it towards the left side of the array. And store index keeps track of where the smaller half ends. Alright. After the loop, the pivot is swapped into its final sorted position, right between the smaller and larger numbers. We then return to that position so Quicksort knows where to split the array for the next recursive calls. And this right here. Oops, just this. Alright, this helper method looks at 3 values and returns the index of the one that's in the middle, not the smallest or largest. It's a smart way to pick a pivot that helps keep the array balanced for faster sorting. Just helps find the median of 3. This right here, the small utility that simply swaps the elements in the array. And finally, we have all the way up here out of the loop. This right here. This, after all the recursive calls, all the sorting, all that, it prints the array and the sorted array. And yeah, okay, let's run it. See how it sorts. It's not really going to show us anything, but we can look at it. Yep, sorted original array and then sorted into the sorted using Quicksort. Pretty cool. Alright. Alright, quick tip. Always remember Quicksort is all about a good pivot choice and divide and conquer. Pick wisely and it's fast, pick poorly and it slows down dramatically, as we covered. Before we wrap up, here's a quick peek into what happens in the real world. Most programming languages don't just rely on one sorting algorithm. For example, C#, Java, and Python, the built-in sort functions, so sort would look like sorts. Built-in sorts functions actually use hybrid algorithms. That means they combine different strategies like quicksort and insertion sort to get best of both worlds. Fast on large data sets and efficient for smaller or nearly sort. Yeah, here are the sorted ones. This hybrid approach avoids the worst case scenarios we've been talking about, like Quicksort's O(n)², O(n)², and ensures your data is sorted quickly almost every time. So while learning these algorithms is super useful, in practice, libraries already have clever tricks to make sorting robust and fast, like hybrid stuff. So that's it for Quicksort. You now know why pivot selection is so important and how it affects performance. Well, that's it for this series on Big O notation. Thank you for joining us in this series, and we hope to see you again in the future, whether explaining quadratics and when they beat O(n) log n, or even just walking you through C#. Yeah, that's it.